Welcome to the Tech and Space Leaders Show, where we learn lessons from leaders of the next frontier. I am your host, Lisa Dreher, and I am really excited to introduce our guest for today, Bob Brumley. He is the co-founder and chairman of CommStar Space Communications, among other things. And I really am pleased to welcome you to the show, Bob.
Thanks, Lisa. I appreciate you inviting me back. I'm glad I didn't make a mess the last time I was on your show. So, thank you very much for the invitation.
Sure thing. It's my pleasure. Maybe we can start by having you go ahead and give us a little bit of background on yourself and CommStar.
Myself basically is CommStar will be my sixth satellite company in my career, and it has a sister company, Laser Communications, and it actually grew out of a project we did with NASA. Thank you, NASA, which was a deep space relay network study. And we realized that there was an opportunity here to apply some infrastructure that the U.S. government had not either contemplated or felt they needed. And that's where CommStar came from. And after it's just for the entrepreneurs here, one of the hardest things about CommStar was finding a name that was not taken or protected. And it took us a week or two to find this name. So we're really pleased with it, and we're pleased with the progress, and we're also pleased with the fact that we think it's going to make a difference.
Absolutely. Yeah, I'm surprised you could do that in just a couple of weeks.
Right.
That can be tough, especially something that you can get the URL on and all of that. So congratulations.
Well, thanks. I'm here to answer your questions. So you give me a 5-10 minute grilling, and then we can turn it over to the audience.
Okay, sounds great. It would be great if you could talk a little bit about the major problem that CommStar is solving.
Yeah, it's really two things. Most of the people who attend your podcasts are pretty knowledgeable, not just about space, but about comms. The two problems, if you will, which we view them as opportunities, are swap, space weight and power, and latency. For all of us who deal with what would be space infrastructure, particularly in the outside of LEO, as things get further away from Earth, and they also have a tendency to get lighter and smaller price per pound of space, you get around the moon or on the moon, and you have reduced your space, weight, and power budget on trades. When you do that, you're also trading off on carrying what would be uh, more powerful, stronger capabilities, either in antennas or optical, which would basically be needed to do a more robust communications link to Earth. That's where we come in. We actually, some of our customer base that we're focused on are those with limited swap, like landers, demos, Pathfinder type programs that are going on and around the moon that have traded off some of their comms capability if they can plan on just relaying to where CommStar is going to be located, which is Earth Moon L1. If you can see it, and you can see it from the lunar surface, if you can see the Earth, you're looking right through L1. So if you can get to L1 from the lunar surface, which is about 39,000 miles, we in turn can take your signal and relay it. So the first thing is we take a lot of burden off of smaller satellite systems, and we pick it up in terms of our own swap. Secondly is latency. Without mentioning a couple of lander accidents, a couple of them had latency problems. Now, not latency relative to, as you all know what latency is, it's basically the time to move a bit of data from point A to point B. There's also latency on upload and downloads. If you're 3,000 milliseconds away from what would be around the moon on bidirectional latency, then 3,000 milliseconds or 3 seconds times how fast you're going means your opportunity to adjust, whether it be software or adjust your landing pattern, becomes difficult, and in some cases fatal. Latency, as I mentioned, is a lander killer. So being closer, 200 milliseconds or closer, to the lunar surface or around the moon means that you can make corrections. You can also do high-speed computing where you would not have that ability if you were computing from the Earth. So those two end up with a need for a solution. How do you solve the swap problem? How do you solve the latency problem? It's infrastructure closer around the moon. You either move all the cell towers and the Earth stations from the Earth to the moon, or else you basically build something near the moon. And that's where CommStar 1 is going.
Wow. Okay. So when you say near the moon, are you talking about launching a lunar satellite? How does this work?
You put up a satellite, as we all know them, and it is a more robust satellite than you would normally deploy on missions like this. In our case, our profile satellite is about 4,500 kg. It is got 21 kW of power. It's a big satellite, and it is very similar to a GEO satellite, except this one would be hosted out at Earth Moon L1. EML1 is about 200,000 miles from the Earth and about 39,000 miles from the lunar surface. So it has so much power, so much capability that it can run both hybrid RF and optical. So it'll do laser comms and RF in a fully integrated system. So if you're operating on RF spectrum, you can connect to it, and then we can basically rebroadcast it just like a GEO does to Earth. We can even rebroadcast it to a GEO that's compatible with us and onto an Earth station. Or we can do optical, where we can optical to the laser light all optical satellite system, or if the antennas are adjusted on Starlink or Kuiper or others that have inter-satellite links, we can basically connect it to them or directly to an optical ground station. This gives lunar comms the ability to network, not just connect, but to network. And number one, and number two, if we use optical from L1 to the Earth, there's no interference issues that you normally get with RF. So you don't have to coordinate. All you have to do is basically broadcast in laser comms or optical beam, and you can go straight to the Earth without the need to coordinate. You do need landing rights, but you don't need to go to the ITU to coordinate.
Wow. Okay, that is a lot. So when you talk about this technology, and you kind of mentioned for landers and being able to really keep track of landers and things like that, what other use cases will this technology be used for?
Well, first and foremost, you're using it whether you're using RF or you're using optical in cislunar. And I should take a step back and say the area we're in is at Earth Moon L1 is in a physical space dubbed cislunar. Behind the moon and on the way to deep space is translunar, but cislunar is that vacuum. We call it the cislunar sea between the Earth and the near side of the moon. L1 is in line of sight of the Earth and the moon, and has a somewhat stable orbit at L1. So as the moon moves around, L1 moves around with it to the Earth. And so if, like I said earlier, if you're on the moon, you can see the Earth, you see L1. If you're on the Earth, and tonight it's a full moon, when you look at the full moon, you can see L1. So L1 is stable, and in a sense that putting a satellite there, you don't have to move it around a whole lot. And from an optical standpoint, that's good because you're not really creating too much onboard problems. So the kind of services you'd have would be, to be blunt, very similar to what you'd have at a AWS hub, or you'd have at a Microsoft computing hub, or a Google hub, or a 5G tower. You can do secure comms, you can do streaming video, you can do even come up with some creative solutions that may address the RF quiet zone on the far side of the moon.
Wow. Okay. So what does it take to make all of this actually work? And even just to launch this satellite?
Well, thank goodness for not only SpaceX, but new launch companies coming online like Ariane 6, the Indian launch companies as well. the CommStar satellite would have to be deployed in what is called a lunar insertion. So we've even talked to some of the new launch companies, Firefly, for example, that could possibly handle the mass and the delta V to get us to L1. So there are options there to get it there. Then once you've got it there, you basically have to maintain it at that location. By maintaining it at a known point, you have other types of missions that cluster around it. So, for example, we have vendors that we've been talking to, Novium Space, for example, on robotic arms, where we think we could use CommStar One not just as a network access point, a NAP, but also as a logistics hub, because we have power to give. We have swap. So we've created a new term, swap as a service. So space, weight, and power, you come up to the CommStar One satellite, and assuming we're integrated on the same standards for tethering and porting between each other, we'd be able to provide you with power, and we can provide you with comms. So it's kind of like an intermediate point, almost like a space station. And you can poise there until you're ready to go, and then you can go on down the other 39,000 miles to the lunar surface.
Okay, so what is your timeline?
CommStar is actually going to be deploying in 2025, this year.
Oh my gosh, that's amazing. That's very, very soon. What role have partnerships played in the development of this entire plan?
Well, as famous writers have pointed out, no man is an island, or no woman is an island either. You can't do any of this stuff without partnerships. You got to have a best in class vendor team. You got to have basically third parties who may be in fact customers, but who in fact would like to test and trial what you're doing first. We call those payload teams. We'll be doing hosted payloads on CommStar. And in addition to that, we also have, since we're a pure commercial company, we also have to basically have a friendly and pro-business regulatory environment. There is a somewhat such environment here. There's also what I'd say a more laissez-faire environment in Europe, and it's just picking the right environment that fits your business model.
Right. So talk a little bit more about that, because regulatory is a big deal, right? It definitely impacts these sorts of missions and rollout of these commercial solutions. How is that impacting your program?
It's not, and we don't expect it will. The general regulatory program is a spacecraft. You have to go to, say, for example, FAA in the UK, CAA, and other regulatory bodies in Europe to get your launch license. And then in addition to that, you have to, if you are dependent on spectrum and you're not a government supported program like CLIPS, then you have to also get your own spectrum. And we have been in the forefront on, as the FT pointed out just a few days ago, that we filed early for spectrum. And we also filed early for a lunar orbit slot at L1. And that allows us to then do planning, again, within the regulatory environment on how we will use spectrum or how we'll use the optical system in balance with our commercial requirements. So regulatory hasn't been yet a problem for us. We do have to have landing rights as we bring traffic back. And so we'll start landing right coordination sometime in the next 3 to 4 months.
Exciting.
So actually, I'm one of the few commercial companies who's sitting here saying I don't have a problem right now with the regulatory agencies.
Absolutely. So I want to end with one last question, and that is, if you could make one prediction about the future of space communications, what would it be?
Oh, that's easy. That is, as with terrestrial data services and communications, the stuff we have down here, the commercial sector is going to dominate communications in space, and particularly initially in cislunar, and then ultimately on and around the moon. It's a natural evolution. It's an extension of what we do down here. There's it's not, to use the trite term, rocket science to do a lot of this. There's no need to build a brand new internet for the moon, when in fact all you need to do is extend the internet as we know it today, and I'm speaking as communications and interoperability, to the moon. New designs, new ways, or new ways of protecting networks are good, but they can also be used as barriers to entry. And so, like when the internet was originally formed, it was left wide open, and that's how we think cislunar ought to be, and of course, lunar comms. So I think the private sector will dominate it, and I believe that it moves faster with what we call basically COTS technologies, hardened for space, faster than a government program would. So the advantage is for the government now is to understand that and get on board. Transportation has been commercialized. Power is going to ultimately be commercialized. And the role of government in communications is ultimately going to be commercialized.
Very exciting. Okay, so actually that brings up another question for me, which is, does this also set the stage for other missions in, deeper space, other locations?
Yeah, we the study that we had worked on for NASA was looking at deep space and NASA's transition from RF only to RF and optical, and mostly that was driven by the demise of the TDRS program, the Data Relay Satellite program, and a lack of infrastructure to replace it. So for deep space, the challenge is there beyond the, it's got environmental, it has a whole bunch of issues relative to swap, et cetera. There's a gravity issue, which kind of surprised me when we first studied it. But with that in mind, the size of the systems to be deployed are very cost effective. You could put a small sat, 100 kg, properly hardened with a single mission on a specific band and send it out into deep space, and you get a fantastic return. Oh, that's what JPL does anyway, right? They do that now, and they've been doing that for 30 years. On the other hand, the instead of just sending one, send two, send three, send four. Sure. If you send more, they can talk to each other. And that's the big delta here, is the future of deep space communications, just like lunar communications, is networking, not connectivity. It's networking. And if you can network, there's no spacecraft you should throw away. You should keep them, put them in a location, or let them come back around and continue to use them as really virtual relay platforms. And NASA does that. They'll bounce a signal off of one to the other to bring it back to Earth. Now we're saying, plan on doing that. Plan on it, and then let the private sector do it. So for, Musk is going to go to Mars. If he, pardon the phrase, it's become a satellite term, so I'll use it. If he poops out little satellites along the way and just distributes them, he creates his own telegraph pole with wire. He's created his own wireless network on the way out. He's going to lose some of them, but they're cheap. Right now his Starlink satellites are running around $200,000 a piece. And since he gives the free launch, that he could basically build an infrastructure, and that's final key here. Infrastructure. Tie it to the infrastructure we have on the Earth, tie it to the infrastructure you have between the Earth and the Moon, and then tie it to what would be the infrastructure in deep space. And I think that works.
Yeah. Fascinating. Okay, so I feel like we've barely scratched the surface, but if somebody wanted to learn more about CommStar, what should they do?
Please don't call me. The person to call is our acting CEO and COO, Matt Zlotnick, that's Zlatnik at CommStar.space. But a lot of you know me, so you can go ahead and contact me anyway, and I'd be happy to talk to you.
And then the website is CommStar.space.
It is CommStar.space.
Got it. Okay, great. Well, Bob, thank you so much for making time to be here today. We really appreciate it. It
My
was
pleasure.
incredible learning what CommStar is up to, and we're really excited to watch as you launch this this new satellite.
Appreciate it, Lisa. Once again, the next time I create a new satellite company, you'll be the first person I call.
Fantastic. Thank you.
All right.